All right, welcome to our next lecture in Intro to Logic and Troubleshooting. Today we're going to talk about tools and test equipment. So here's a brief outline of the discussion that we're going to have today. We're going to look at tools and different testing equipment for different properties of a machine or of a system. So we're going to look at tools where you can test the electrical properties, mechanical properties, and thermal properties. And now these are all tools that are going to go in our engineering toolbox. I'm bringing back our little tiny 3D printed toolbox. We need to fill this thing up with some actual tools. Okay, so first, troubleshooting diagnostics. So first and foremost, as technicians and as troubleshooters, it's our job to identify and resolve the technical failures. So this requires a little bit of engineering detective work. Engineers and technicians need to do this detective work in order to identify what the root cause of the failure is and prevent it from happening again, and fix it, obviously. So you want to use the right tool for the right job, but that takes experience and exposure to these tools. So it's only after having used the tool or having been informed how the tool works or when to use the tool will you actually know how to use the tool. One thing I also want to point out too, so most of the systems and most of the components within the systems that we're going to look at have multiple connections. So there's typically some sort of input information. It tells the component to turn on, to turn off, and then oftentimes there's information that's sent back to some other higher order control system, a DCS system. And so when we go to troubleshoot, a lot of times there's multiple electrical leads coming in and out that we're going to have to look at and investigate. All right, so let's look at electrical components and how to troubleshoot them. All right, so first and foremost, let's just review what a simple circuit looks like. So I have a couple different versions over here. I have a battery, and then the battery is powering this light bulb. Easy enough, right? Okay, well, if I were to convert this into a more engineering type schematic, it would look like this. There's a voltage source. It's got a positive and a negative side, and the current flows from positive to negative through the conductive wire, through whatever component is in the circuit, the load, and then back through the power supply to the negative side. So the power supply itself provides an electrical power in a stable form. And so this is something that's like non-changing, or very little changes, and this provides stable electrical power to the circuit. The other obvious part is this just conductive wire. So we need metal wires in between electrical components in order for electricity to pass through. It's kind of common sense, but this is an introductory class, so common sense is something I'm assuming that none of us have, me included. And then just let's look at simple circuit properties. So we looked at Ohm's law at the very beginning, and we talked about voltage, current, and resistance, but let's give them good definitions here. So the voltage is the electric potential, meaning this is the energy that's associated with the circuit. The current is the flow of charged particles, and the resistance, or a resistor, is an opposition to the current. And what a resistor does is basically converts electrical energy into thermal energy. And so there's a voltage drop across a resistor. The SI units for voltage are volts. The SI units for current are amps or amperage. And then the SI units for resistor are ohms. And there's a good analogy that's often used between a circuit, an electrical circuit, and a water flowing through a pipe or water flowing through a channel. So basically, I have this little doodle down here, and this is representative of this analogy. So current is the flow, is the water flow. The voltage is the water pressure. That's what's providing the energy to actually push the water through the pipe. And then the resistance, or the resistor, impedes the flow. So it's something that's restricting the flow. So here I have the little volt guy is pushing my current, my amperage, through this restriction that the little guy with the cowboy hat, this is the resistor, is setting up. So he's setting up a kink in this hole. It's resisting, it's impeding flow, but the voltage provides enough energy for the current to flow through. Okay, so now let's actually look at some tools and how we're going to use these tools to actually troubleshoot these electrical systems. So the first and probably your bread and butter really, this is a multimeter. So a multimeter can be used for DC or AC circuits, and they're used primarily to measure voltage, resistance, and current. And now they have a few other features we'll talk about, but there's two basic types of multimeters. So first we have this one here. This is called a volt ohm meter, and you might find this like in your grandpa's garage or something like that. Or I mean, I have one, but just because it's fun to have. I like older. Like scientific equipment, but these are largely outdated. So they're analog, meaning there's an actual meter rather than a digital readout or an actual dial, and they can be found typically with legacy equipment, but they've been largely replaced with these digital multimeters. And the digital multimeters are nice because they have the digital readout, they have improved accuracy, and they have many more functions. But again, like I said, they effectively do the same thing. So here I have a nice doodle comparing them side by side. They both have a hot or a red. So the red lead right here, this probe, is for the positive side or the hot side. The black probe is for the negative side or the common. And here's just an example. So this is the example that we're going to talk through. So this one right here, this is probably the most basic digital multimeter you can get. So you can see mine. This is the one I had laying around. So this is $12, and you can get it anywhere you want. Now, I don't know that I would use this necessarily at a job site, but around the house or something like that, the little $12 guy is fine. And it's good for our discussion today. So this comes with accessories and functions. We're going to talk through the functions of this multimeter because the functions that this multimeter possesses are essentially what all other multimeters possess, and then maybe some higher order functions. So right here, I have some sort of component. It's got a positive side, it's got a negative side. I have a test probe that goes from the positive side here, and I put it in contact with the lead on the positive side of the resistor or whatever this component is here. And then I have a black probe, so this is my common or the negative side. And then let's look at all the different functions. So first I have DC voltage. I can measure the DC voltage. I can measure the resistance of a circuit or of a component. I can measure the AC voltage for if I have an AC circuit. I can do a battery test. I can measure DC current. I can do a diode test. And then finally, I can do a transistor test, and this is the socket that's used for that. So basically, there's another component that goes in there, and then we do that to test transistors. But really, we're largely considered, or largely, we are going to largely consider these four functions, and these are going to be our primary functions for this device. So measuring DC voltage, measuring the resistance, measuring the AC voltage, and then measuring the DC current. This is going to get us most of the information that we need. And each of these has a range at which they can measure. So you set the dial, and according to the range that you set, you get a measurement that's within a reasonable value. So if I have something that's, in this case, I have a very large spread of DC voltages I can measure. If I have a very, very small voltage, I don't want to be working at a very large range because I won't get a very accurate measurement. So I change the range down to something that's more appropriate for a smaller voltage, and I'll get a more accurate measurement. So I'll get more significant figures for my measurement. So here I have ranges that go from 200 millivolts all the way to 1,000 volts for DC voltage. For resistance, I have anywhere from 200 ohms to 2,000 kilo ohms. So this is a significant increase in resistance. It's a very large resistance. For AC voltage, I have just two options. I have 200 volts, so 0 to 200 volts, and then 750 volts, so for larger than 200 volts, but less than 750 volts. And then for DC current, this is going to be very small. So this goes from 200 microamps, to 200 milliamps. So typically, many of these devices and many of these sensors that we're going to look at, they give information, or they're powered by some control component, but basically they run on 4 220 milliamps. So if it's being provided 4 milliamps, it's at an off state. If it's being provided 20 milliamps, it's at a total on state. Or if I have a measuring device, a sensor, and it's measuring, and I measure the current from it, and I measure 4 milliamps, that's typically the lowest. So that's the zero, or whatever the bottom measurement of that device is, and then 20 milliamps would be the maximum measurement that the device can make. All right, next we're going to look at oscilloscopes. So this is the other major component that you want to use for electrical troubleshooting. And they provide a great visual representation for electrical signals. So they're very good to use for AC circuits. So there's two different kinds. We have a handheld scope and a bench scope, but they basically provide the same features. Obviously, you're going to get a little bit more functionality with the bench scope, but the handheld scope does provide a nice visual representation of what the wave function looks like. So let's look at these. I mean, first, when I look at this thing, this looks a little scary, right? I mean, there's a lot going on here. This has got 17,000 different waves. This has got a whole different, two different things going on. This has got, multiple ports. What the hell am I looking at? Well, okay, let's just make it simple. So there's the display, and on that display, all we're doing, or typically all we're showing, is voltage on the y-axis and time on the x-axis. So we're showing the wave function voltage as a function of time. Then I also have these two controls here, so dials. So I have basically windows for the x and y axis, and I have typically a coarse tune and a fine tune in order to get the window to where I want it to be. And then I have some trigger options. So basically I can trigger when I start to take this measurement in order to, basically record the wave function here. There's also multiple inputs. So we saw in the previous, this guy here, you can see multiple wave functions here. And I get that by plugging in multiple inputs, multiple ports. And then, finally, there's just a few other kind of lights and buttons that kind of indicate, power on, power off, and then some functionality. But this is the basic idea of an oscilloscope. You'll really get the hang of it as you use it. All right, next we're going to talk about jumps and traps. So these are used to temporarily bypass a component, and it's in order to test if the power being supplied by the control device is accurate. So there's three main types, really. There's a lamp type, fuse type, and a relay type. And really, so the lamp type is just an indicator light. It just shows you, okay, yeah, power is coming. A fuse, this fuse trap here, this is set up so that if too much power is coming to my device, the fuse will blow. And the fuse blowing indicates to me, okay, this is getting too much power. And an example of that would be these blade fuse boxes. So these blade fuse boxes are used to test fuses in cars, test circuits in the field. So this is something that you'll be using rather often. So this gives you the opportunity to test multiple different fuses, so basically multiple different currents, to see what you're actually getting into the system. It also allows for you to set up multiple circuits and test multiple circuits at the same time, and gives you a lot of information about the circuit without having to, basically destroy it or take it apart and cause yourself more work than necessary. Another thing that we're going to look at is insulation testers. So these are referred to as megometers or just megers, and they're used to detect insulation problems in wirings and windings. So here's an electric motor, and an electric motor works by basically you wind all these copper cables together and you put them in an array. And the way you put them in an array, combine that with some sort of magnetic component, and basically that's how an electric motor works. So electricity and magnetism are, related to one another. We'll actually talk about that in the next slide. But this device works by providing a large voltage and then over a minute or two, time averaging and giving you some information about the resistance that it measures. If there's an issue with the windings, so if there's connections where there shouldn't be, this will inform you that, this is not wound correctly. This motor is going to fail if we turn it on. All right, so then non-contact equipment, excuse me. So this is used when you cannot connect directly to electrical contacts. And these all work the same way. So like I said, electricity and magnetism are actually the same thing, electromagnetism. And in reality, how this works is when I pass a current through a wire, so this is a wire, this black arrow is a wire. When current flows through, I have electricity and I have particles flowing through, it generates a magnetic field around that wire. And that's shown here as these circles and labeled as B here. But basically, like I said, electricity and magnetism are one and the same. So the stronger the current that goes through this wire, the larger the magnitude of the magnetic field. And if I can measure that magnetic field and measure how strong the magnetic field is, I can infer how much current is going through this wire. So that's effectively how all of these devices work. One of the most important ones is this clamp-on amp meter. So this is really useful when you're working with high power stuff that you don't really want to probe, or wires where you can't probe. And basically you just clamp this around a big cable and it'll give you an approximation for the actual amperage that's going through that cable. A few other examples are simply a magnetic field detector and then underground cable detectors. So a lot of times you want to know, hey, is there a cable underneath, where I'm digging or where I'm working, or trying to find it so that you can service it. That's how these underground cable detectors work. And then another very simple one. So there's these voltage probes. And so this is just gives you a go or a no-go. And there's two different kinds. This one is an actual contact probe, but the one I'm showing here is a non-contact probe. And this tells you simply, is the circuit energized? And this is something you want to use when you start because you want to know what you're working on. You want to know if the circuit's actually energized or not. And then you can use this while you're troubleshooting to basically characterize the circuit as you make steps towards the repair. Are different parts of it now getting electricity? Are certain parts still lacking electricity? And it just tells you, okay, yeah, power is being supplied here. There is an electric potential here. All right, so now we're going to look at mechanical tools. So tools to measure mechanical properties and basically diagnose systems that way. So one thing that we're all familiar with, whether you've called it this before, is a tachometer. So this is something that measures the speed of an object, and you've seen this because it's in your car. So your revometer in your car, which just measures the revolutions of the crankshaft per minute, so RPM, this is a form of a tachometer. And how these work, there's two different kinds, it's shown here, is I have a contact tachometer and a contactless tachometer. The contact tachometer interfaces with whatever object I'm measuring. So in this case, I have a motor here and I have a shaft coming out of this motor. I interface with that shaft with my device. As the shaft spins, my device, little probe here, spins with it, and it just simply tells me how fast is that spinning. And then you can do the same thing with a photo tachometer. And this just uses light to basically, like I said, measure the same thing. So it sends light pulses or laser pulses at the same frame rate or frequency as the rotation in order to measure the rotational frequency. So this will give you the same value, just in a different way of measuring it. And then, okay, so sometimes we have machines. So here I have an electric motor. This electric motor is connected to this shaft, and this shaft is connected to this fan blade. Now you see how this fan blade is kind of wobbly and off-centered? This is not good. If I let this run and I keep this going, this is going to cause problems. We're going to have, the shaft is going to start to bend, then I'm going to have stresses here at this adapting piece, and actually all the way back into the motor, and this is just going to cause problems. I'm going to have a failure for sure. So we need to measure the vibration or the translational component of machines while they're operating, and to do that we use these vibrational sensors. So vibrational sensors measure the amplitude and frequency of the vibrations. So as you run a machine, it always vibrates, like a pump or Even you can think about like the compressor on your air conditioning unit. You can feel it vibrating. Anytime it's operating, there is some sort of vibration. However, if it's vibrating to an excessive point, it's going to cause some failure. It's going to put stresses on other components or things it's connected to, and it's going to lead to a failure in the system. So we want to detect any sort of imbalance, misalignment, bearing failures immediately so that they can be replaced or repaired so that doesn't lead to a larger failure down the road. And there's 3 different types of these vibrational sensors. It's not really important that you understand what these are, the different types, but just so you know, there are 3 types. They are an accelerometer, a strain gauge, and an eddy current gauge. So 3 flavors that they come in, but basically, you'll have these handheld components that just set up, and there are ports in the machine. You plug it in, and you're able to actually record the vibration of the machine. All right, so then we're going to look at pressure gauges and pressure measurements. So in many systems, there is a high pressure or low pressure side. In order for water to flow through my faucet, there needs to be some sort of supply of pressure, and that's done from a big pump house, like somewhere in the city. I don't know. I don't have a pump here, but I have city water. But basically, we need to be able to measure pressure, and in order to do that, typically we use this analog pressure gauge. Now, these analog pressure gauges are nice because they're reliable, but in systems where something's continuously operating, we typically have pressure transducers, so electric pressure sensors. One way to calibrate those and make sure that they're working is to compare what they're measuring with this analog pressure gauge here. So this kit right here comes with 17 different fittings or whatever, and it does so because many different systems use different fittings. There's English versus there's English size. You have things that come in 1/4 inch or 1/2 inch or 3/8 inch, and then there's also metric fittings, so things that come in 11 millimeters or 13 millimeter. They're different size fittings, and having all of these available will allow you to access whatever that system is using. Okay, so then finally we're going to look at thermal components, so the temperature of a system. So measuring the temperature of a system provides insight. So if the temperature of something is very hot or hotter than it should be, this is an indication that some sort of cooling system has failed, or there's not lubrication where there needs to be, but you could be headed towards a failure. If a temperature is lower than it should be during operating temperature, this could be a sign that it still needs to heat up. So when you start your car in the winter and it's super cool, that's not very good to just go ahead and drive right away. There's oil in your car and there's lubrication in your car that helps basically metal components that are sliding next to one another or in contact with one another. It makes it easier for them to move. And if you're starting your car right away in the winter and it's super cold and you're driving it, you're not allowing for that fluid to warm up enough to provide the lubrication that your car really needs. Now, eventually it will after you start driving it, but it's just putting more wear on your car than necessary. So there's many different ways to measure temperature. In fact, in the research lab I worked at University of Wisconsin, we had a laser measurement technique, and then at MIT, we used an infrared measurement technique. But we're going to talk about a few other ones that are more applicable for field work. So, there's basically there's 3 that we're going to look at here. So a thermometer, we're all familiar with thermometers. So a mercury thermometer works simply. And it's not mercury anymore, but it's got some fluid in it. And basically, as it heats up, the fluid expands. As the fluid expands, it fills this cavity, and then that's calibrated to indicate the temperature that the fluid is. There's a resistive temperature device, RTD. So this is a little circuit element, typically made out of platinum. And basically, the resistance of the platinum resistor, the resistance changes with temperature. So the resistance of the device changes with temperature. Now that means that I can measure the resistance at different temperatures or measure the resistance and infer the temperature. So it'll be one resistance at this temperature, another resistance at some other temperature. I make a calibration curve, and then I can always measure the resistance at any time, and I can get temperature from that resistance measurement. There's also what's called a thermocouple. So this is comparable. This is something similar. So a thermocouple works by, it has two separate wires, and they're made of two different materials. They're welded together at the tip here, and this is called the hot junction. And basically there's a voltage drop across this connection here. And the voltage drop across that connection is associated with the temperature. So it changes with temperature. And so these are also calibrated. These RTDs and these thermocouples typically can be calibrated from the manufacturer. They can also be calibrated in-house using like a water bath or something with a known temperature. And then we're going to look at these just because I think they're awesome. So IR temperature sensors. So this is something that's really useful and basically can provide a lot of information without necessarily having to probe anything. So you can think like night vision. You know, these work basically like that. So everything gives off this infrared light that we can't see, but it's associated with energy. You know, that there's heat coming off of me and anything that is at a wavelength that our eyes cannot actually catch. And so this is nice. Like I said, this is a non-invasive technique, and there's a few different like kind of probes and styles. So this one down here is just an Omega like little gun, and I point it at whatever I'm trying to measure the temperature at, pull the trigger, hold it for a few seconds, and then it tells me, this digital readout tells me what the temperature is. Now, FLIR makes these really cool infrared cameras. So these infrared cameras will show me exactly where there's a hot spot. And this is really nice when I'm troubleshooting like these electrical panels. This indicates, okay, there's an issue there. This right here, that shows me that's where the issue is. So these are very useful, very cool. These FLIR components are typically pretty expensive, but like I said, like very useful. And then these Omega, this Omega one was I think $400 on Grainger. All right, so just a summary of what we talked about today. So first and foremost, use the right tool for the job. So again, as troubleshooters, as engineers, our job is to discover and repair, the root cause of whatever is failing. So in the discovery process, we need to take diagnostics, and we do that using the test equipment that we talked about today. For electrical components, we typically measure voltage, current, resistance. For mechanical components, we measure motion, pressure, and then we also measure the temperature of a system, because the temperature can give us a lot of information about the overall health of that system. All right, thank you very much, and we'll talk to you soon.